Hello friends, welcome to Hydraulics and Hydraulic Machines class. In this lecture, we focus on three topics, but all these three topics address one issue only. Number one is what is the maximum suction lift or what is the maximum suction height? This is the first thing. How much we can keep? You can ask me. Suppose when the water is there in the well, from there to the inlet. So that vertical distance is what we call it as suction head. So what shall be that maximum suction head? Suppose if we go on increasing that, will the pump lift? Definitely no. The pressure at the inlet of the pump, the pressure at the inlet of the pump should never be equal to or less than the vapor pressure of the liquid. Every liquid has some vapor pressure. Water also has some vapor pressure, which we have already studied in fluid mechanics. So, the pressure at the inlet, the pressure at the inlet of the impeller, at the center of the impeller, should be more than the vapor pressure of that liquid. Then only the pump will lift the water. If it is less than the vapor pressure of the flowing fluid or vapor pressure of that water, then actually the water turns into vapors and thereby cavitation starts and the entire impeller gets damaged. That's why we need to know what is the maximum permissible suction head that we have to do as the first topic. The second topic is net positive suction head, NPSH. This is commonly people call it as NPSH, net positive suction head. This also is a definition which really helps in prevention of cavitation. So that is the second thing. And closure of this, the third one is what is cavitation? I don't want to define again and again, but how you can prevent cavitation in the case of basically the centrifugal pumps. If cavitation occurs, how basically the impeller get damaged. Already I have shown number of figures. Even at the beginning of this lecture, you can see the photos, how cavitation really affects the entire impeller. The impeller, how it got corroded, how it got damaged, how it got basically what you call it as its efficiency being reduced. So all that is because. So centrifugal pumps, we should never permit cavitation takes place. So this is the today's focus actually. So let us take one by one each other and move forward. So the first topic for us today is maximum suction lift. Suction lift is nothing but suction head. In other words, maximum suction height. How much? What is the equation for it? That is what we want. You know already what is suction lift. Suction lift or suction head. Already go to the figure and just check back once again. It is represented by Hs and it is nothing but actually the vertical distance from the center line of the pump, center line of the pump to the water surface, to the water surface in basically in the sump. Sump means the storage from where we are lifting water. So this is what we call it as Hs. Suppose if I take, just for understanding sake, I will draw the figure also for you. Suppose you take, this is the shaft, right? So this is the impeller, and over the impeller we have the casing. This is how the casing is. And if I take it, suction pipe goes like this, and it will be kept in the water from where we are lifting. So this is the water surface from where we are lifting. So I call this as actually this as the water surface, and this point I call it as the pump inlet. I call it as section 1. Okay, this is the thing. And now basically, so this is the free surface. Now this is what we call it as the velocity Vs, and this one I told you already, Hs. Now what I will do is I applying the Bernoulli's equation, simple things, applying the Bernoulli's equation. What are the 2 points actually? One is free surface and pump inlet. Between these 2 points, I am applying the Bernoulli's equation. What is the pressure here actually? The pressure here is nothing but atmospheric pressure, Pa by gamma, plus what is the velocity in suction pipe? Vs square by 2g, plus here the free surface itself, this itself is considered as datum. So therefore the datum head, whatever I write, z is equal to 0. So that will not be there at all, right? And if I take velocity here, not in the pipe, velocity here, I will take it at the free surface. What will be the velocity? Here the velocity is also 0, but with this pressure, if it enters into the pipe, it will be Vs. So initially when I apply here, the velocity is equal to 0, P is equal to Pa at this place, and Z is equal to, if this itself I consider it as that, then naturally. So therefore, if I take it is equal to, then what is here? It is P1 by gamma, plus basically if you take it, what is Vs actually? It is Vs square by 2g, plus actually datum is how much actually? Hs, plus what is the loss? The loss, head loss in suction pipe. So therefore I can write Pa by gamma plus 0 plus 0 is equal to P1 by gamma plus Vs squared by 2g plus Hs plus Hfs, because the loss is nothing but the friction loss. So if this is the case, now if I write what basically, because you remember the velocity at free surface is equal to 0, and considering free surface as datum, z is equal to 0. So this is what I have written there. So from this if I calculate what is P1 by gamma is equal to PA by gamma minus of Vs square by 2G plus Hs plus HFS. What this equation will tell to you, when I see this equation, what it will tell, P1 by gamma is what? The pressure head at the center of the pump, at the inlet of the pump, is equal to atmospheric pressure head minus something. It is minus something. Vs is velocity head. So automatically it will be positive. Hs is suction head, which you are already seeing it, it is positive. HFS is friction loss FLV squared by 2GD. That is also positive. So that means all this quantity is positive. So if that is the case, so the pressure head at the inlet, at the inlet to the pump is equal to atmospheric pressure head, atmospheric pressure head minus all this, right? So therefore, here this pressure head is less than atmospheric pressure. That is equal to, it is vacuum pressure. So kindly remember, so in the suction pipe, what pressure will be there? It is vacuum pressure. It is less than atmospheric pressure. So this is the point you should remember actually. Now the condition, let us write actually. What is the condition for maximum suction lift? Here it is the pressure head at inlet basically should not be less than, should be always greater than or equal to the vapor pressure head of the flowing liquid. If the flowing liquid is water, then you should write vapor pressure head of water flowing liquid. In limiting case, because I want maximum, in limiting case, the pressure head at the inlet, the pressure head at inlet then should be equal to the vapor pressure head of flowing liquid. Next question immediately you can ask, sir, if it is less than that, what will happen? If it is less than that, please remember that then there will be no question of lifting of water. First thing. Second thing is, initially, even if it starts lifting, actually, automatically the impeller gets damaged. So that is why we will not allow at all. Then first thing is, so that means the P1 by W gamma is equal to, it is PV by gamma. This is what the for the maximum suction lift. What I have shown till now, first I showed to you that the pressure at the inlet of the pump is equal to atmospheric pressure head minus something. That is why it is less than atmospheric pressure. It is vacuum pressure. Now, what is the limiting point to it? It should be always greater than, the pressure head at the inlet should always be greater than the vapor pressure of the liquid. As long as the pressure head is greater than vapor pressure of the liquid, there is no problem at all. Nothing. Automatically water gets lifted up, everything flows smoothly, and the pump will get maximum efficiency. But if suppose if the pressure head at the inlet is less than vapor pressure of the flowing liquid, first problem that you get is automatically, naturally, the cavitation process starts. When cavitation process starts, the impeller gets damaged. When the impeller gets damaged, the efficiency of the pump drastically fall down. So that is why we need to keep at the maximum suction lift should be such that the pressure head at the inlet of the pump is equal to the vapor pressure head of the flowing liquid. That is what I have put. So taking this into account, so now already we know that actually what is the equation we know. Already we know what is that we know. P1 by gamma is equal to, sorry, P1 by gamma is equal to, right, Pa by gamma minus what is the other thing that which we have done previously? It is Vs squared by 2g plus Hs plus Hfs. This is what we got already. Now this P1 by gamma should be replaced by Pv by gamma. That's what for maximum suction lift is equal to Pa by gamma minus Vs squared by 2g plus Hs plus Hfs. This is what I have done. Instead of P1 by gamma, I put it. Now what is this PV by gamma? It is nothing but the vapor pressure head is equal to Pa by gamma is nothing but actually atmospheric pressure head minus Bs squared by 2g plus Hs plus Hfs. My objective is I'm trying to put everything into what I call it as into heads. So now what is here? Because finally I want the suction lift, maximum suction lift. That is what my objective. So if I want maximum suction lift, that is what we call it as Hs. So if I bring Hs on one side, actually now this is Ha minus, actually if this goes inside, Vs squared by 2g plus Hv plus HFS. This is the final answer actually. So this is the equation that which we need to derive for the maximum suction lift. So this is the equation for the maximum suction lift for a centrifugal pump actually. The suction head HS should be basically suction head should be less than this value. This is the maximum suction lift. So generally any of your suction head HS should be always less than the above value which is obtained from this equation. If suppose if suction height if suction height is more than the value based on the above equation, then vaporization starts and which leads to cavitation. So this is the important point. So we have learned this from two angles. I showed you actually the pressure at the inlet P1 by gamma is equal to atmospheric pressure head minus something. That something is Vs squared by 2g plus Hs plus Hfs. And what is the maximum suction condition for the maximum suction lift is equal to P1 by gamma is equal to PV by gamma. So therefore substituting that PV by gamma is equal to PA by gamma minus Vs squared by 2g plus Hs plus Hfs. Therefore Hs is equal to Pa by gamma minus Vs squared by 2g plus PV by gamma plus HFS. So in terms of H, if I write this is atmospheric pressure head minus Vs squared by 2G plus this is vapor pressure head plus HFS. That's what is this. So your Hs always should be less than the value obtained through this equation. So this is completed. Next we go into our next topic. What is net positive suction head? That means NPSH. An excellent bit actually. What is NPSH? So generally this NPSH is being used. NPSH, this terminology is used by pump industry. The pump industry, the people will use this NPSH actually more. So what is this actually? This actually the minimum suction conditions. The minimum suction conditions are more frequently specified in terms of NPSH. This is how generally the industry people will tell it. What is that? Let us take it actually. NPSH, let us define what is NPSH. NPSH actually it is defined as the absolute pressure head. Please see, absolute pressure head at inlet, because we all know that at the center of the pump it is only the vacuum pressure. The vacuum pressure, rather than writing minus, I am writing it as absolute pressure head at the inlet minus vapor pressure head plus plus velocity head in suction pipe. If I write in the form of equation, NPSH is equal to, it is basically P1 by gamma minus PV by gamma plus actually Vs square by 2G. This is what the definition of NPSH actually. We already know that, we already know that Already just now we have done it. P1 by gamma is equal to PA by gamma minus Vs squared by 2G plus Hs plus HFS. Right? If suppose I substitute the same thing here. So NPSH is equal to, substitute in that actually slowly. First P1 by gamma means PA by gamma minus Vs squared by 2G plus Hs plus HFS, all in brackets, minus PV by gamma plus Vs squared by 2G. So this minus Vs squared by 2G plus Vs squared by 2G gets cancelled actually. So this term and this term will cancel actually. Then the remaining things I will write. NPSH is equal to PA by gamma, like regular atmospheric pressure head, minus, right? What is it actually I should write? PV by gamma means what I can write? PV by gamma is nothing but actually H vapor pressure head. That is what this is, atmospheric pressure head. This is vapor pressure head minus HS minus HFS. So this is the thing actually. So NPSH, this is basically, it is equal to atmospheric pressure head minus vapor pressure head minus suction head minus friction basic loss in suction pipe. This is used only to understand what is the suction lift, how it is. So that's what the industry will use for this, for that. Again, NPSH is also one more definition we can write. NPSH can also be defined as NPSH can also be designed as it is the total head required. It is the total head required to make the liquid to flow through suction pipe to the impeller. For any pump installation, a distinction is made between the required NPSH and available NPCH. Normally, what is more important is basically for any pump installation, when you are doing any pump installation, when you are doing it for any pump installation, a distinction is made. A distinction is made between, there are two things here. Number one is required NPSH, and number two is available NPSH. This required NPSH will be given by the pump manufacturer. Given by the pump manufacturer. And this available basically is determined by experiment. Determined by experiment. So generally what we will do is, for generally if you want to determine what is this NPSH, what we do, the pump is tested and, and minimum value of HS is obtained, at which the pump gives you the maximum efficiency, right? Without any cavitation, because the problem is that actually. So that we will take it. So the required NPSH varies with the pump design. This depends on the required NPSH, always depends on the pump design. Pump design, number one, speed, capacity. These three actually determines the required thing, whereas this has to be determined for based on the suction lift criteria. Suction lift criteria. Final thing is, if suppose you don't want cavitation, for cavitation free or no cavitation, what is the condition? The available NPSH should be greater than the required NPC. All this is only you understand two things now we have solved. The maximum suction lift, my objective is to avoid cavitation. Again here the NPSH is also keeping in mind cavitation. So The for basically required NPSH is given by the pump manufacturer. So when we purchase the pump, that data is known to us, and the available NPSH is based on the suction lift criteria when we are installing it. So now take it. Always your available NPSH should be greater than this basically required NPSH. So as long as you maintain, there is no cavitation in the case of centrifugal pump. So this is the second topic. And last topic is what is cavitation in centrifugal pumps? Cavitation in centrifugal pumps. Again, I just for your just reminding sake, what is cavitation? Number one is when the pressure at any point in the flow reduces to vapor pressure of the flowing fluid, vaporization starts. When these vapor bubbles go basically into a high pressure region, they collapse. When the collapse occurs, the surrounding fluid rushes into it and apply high impact pressure. For example, if your bubble is close to the boundary, then naturally that impact pressure is applied on the boundary. When the impact pressure is applied on the boundary gets damaged. So that's why for in three words, formation of the bubbles, collapse of the bubbles, traveling of the bubbles, and collapse of the bubbles leads to finally the cavitation. So all this cavitation phenomena depends on which factor. It all depends on only the suction, basically the pressure at the inlet of the pump. That is the thing that is which really because we get only vacuum pressure or suction pressure only on the suction side of the pump. So that's why from what you call it as at the entry point, the pressure is more than atmospheric pressure in the sump. But from there, when the water is being lifted, when the water moves upward direction, the pressure goes on decreasing and the pressure will be minimum at the inlet of the pump. So we should see that the pressure at the inlet of the pump should never be equal to or less than the vapor pressure of the flowing fluid. It should be always greater than the vapor pressure of the fluid. So this is what. Then you can ask me how you know it, because pump is a sealed thing, because the inside impeller is there, outside casing is there, all is airtight completely. So we don't know initially what happens inside. But the problem is if we don't recognize this, now what happens, because that is why when you are installing itself, you should really make it that available NPSH should always be greater than required NPSH. If you don't follow that, what will happen? Slowly the impeller basically, because at the what is the at the pump inlet, actually the impeller slowly gets corroded, the impeller slowly gets damaged. The moment impeller starts getting damaged, automatically the efficiency of the pump drastically comes down. So like in the case of turbines, what is the factor that we take it? We know there are two things actually. One is critical cavitation factor, because we have done in turbines also critical cavitation factor, and second one is Thomas cavitation factor. Thomas cavitation factor. Kindly remember that actually this Thomas cavitation factor sigma and critical cavitation factor sigma c, sigma should be always greater than sigma c. Then only there will be no cavitation. And already last time I mentioned, always sigma will be obtained based on the conditions in the field at that time, right? There are different, even in the turbines also, we have given the equation for Thomas cavitation factor. Whereas critical cavitation factor, naturally, that is depends on the specific speed, and that equation we have given. So now here also I will give you both the things actually if you take it. Now let us take it. What is Thomas cavitation factor? Thomas cavitation factor, which is denoted by sigma. Sigma is equal to basically it is atmospheric pressure head minus basically the vapor pressure head minus suction head minus friction loss in suction pipe divided by the manometric head. This is what we call it as basically this Thomas cavitation factor. The entire numerator, if you study once, it is nothing but NPSH divided by a manometric head. So this is the Thomas cavitation factor. Sigma is equal to NPSH divided by manometric factor. This you can calculate. Then critical cavitation factor, which depends on the specific speed of the pump. Critical cavitation factor, it depends on the specific speed of the pump, and the equation for that is equal to sigma c is equal to 0.103 into ns by 1000 whole to the power of 4 by 3. This is the equation for critical cavitation factor. So now for cavitation free pump, what is the condition? Sigma, Thomas cavitation factor should always be greater than basically critical cavitation factor. So, but in the last topic, I did not again explain to you basically again what is cavitation and all. But one thing you remember, so because of cavitation, in the case of centrifugal pumps, which component gets damaged, that if you remember, that will be fine. So which component actually gets damaged because of the centrifugal pump? So you know that which component, that is the impeller gets damaged, then the boundary of the casing gets damaged, the inside boundary of the casing gets damaged. So that's why cavitation should not occur. Compared to the turbines, the centrifugal pumps are more vulnerable for cavitation. So that is why you need to study these three things. What is the maximum suction lift? What is NPSH? And what is Thomas cavitation factor? And what is critical cavitation factor? The maximum suction lift is from the angle that what is the pressure at the inlet of the pump. And then second, this is negative pressure. That is vacuum pressure. That is less than atmospheric pressure. But to what extent it is? Second one is what is NPSH? Again from the same point actually. And third one, how to get Thomas cavitation factor? NPSH divided by manometric head. And critical cavitation factor always depends on the specific speed, whether it is turbine or pump, it depends on the specific speed. So this is the nutshell of the basically short note says. One short note says first what is the maximum suction lift. The second short note is what is the second thing is what is NPSH. Third one is we are studying what is cavitation in the case of turbine. So these are the three things. With this, I will stop this lecture here. Thank you so much for your patience. Thanks a lot.
Like, share, and subscribe. Hit the bell icon for more updates.